want capacitor to discharge slowly. Then only we can say that V in plus Vp is V up, right? Or Vf. So in order to make sure that it's holding on to that Vp voltage for a long time, they need long or maybe large time constant. What is the time constant of a circuit, RC circuit? The time constant of RC circuit is the resistance times the capacitance. So the time constant says how fast or how slow a circuit discharges. So if you look at the RC circuit, so if you look at the voltage across the capacitor, the voltage across the capacitor will slowly reduce. It will not, it will just reduce to zero at some point. If you don't do anything, if you have a RC circuit, you somehow charge the capacitor to a value of Vp, the capacitor voltage will not remain Vp forever. It will slowly discharge. Some current will run through the resistor, and that current will dissipate energy as heat, which means the capacitor will slowly lose its voltage. So this is how your voltage will be dissipated. Now, how fast or how slow is the dissipation? That question can be answered by looking at the time constant of the circuit. So if time constant is large, then your voltage will decrease slowly. If time constant is very small, then voltage will reduce very fast. So in order to hold on to this voltage, I want a large time constant. So that large time constant, as I can see here, I can see that the time constant is, so basically if you go make the time constant larger, you get more and more curves like this. So curves will become flatter and flatter, so slower discharge. So the time constant tau is RLC. So if you increasing, so this is increasing tau. So increasing tau. So tau is RLC. So we want large tau. How do I make tau large? I have two choices, right? I can make RL very large or I can make C very large. But the thing is, I want a circuit that holds on to the charge. I want an RC circuit that holds on to the charge or holds on to the Vp voltage for a long time. But I also want an RC circuit that charges very fast. So what would happen is that no matter what my RC values are, what my time constants are, at some point or the other, eventually the capacitor is going to discharge considerably. At that point, suddenly my diode would become forward biased. In that situation, again, I have the older situation in which at the very beginning of the negative half cycle, whatever we saw, suddenly the diode is acting as a short circuit, so I'm not getting anything at the output. So that shouldn't happen. I don't want that to happen. Even if that happens, that should happen for a very short time. So the capacitor should be able to charge to the peak Vp voltage very quickly. And that can be done if I have a capacitor with a small value. So what I want to do is I want to keep the capacitor not very large. So I don't want to make the C value very large, but I want to make the RL value very large. So basically what I would do is use large RL. Eventually what we want to make sure is that ensure RL times C is greater than 100 times T, where T is the time period of the input waveform. So I want to have RL times C, the time constant, is greater than 100 times T. And so, and what is T? T is my time period. So this is my V input. So this V input, this duration is T. This is T. So this is my time period. So this T as compared to the time period of my signal, RLC should be very large. So basically RLC should be at least 100 times the value of my time period of the signal. So basically the signal fluctuates fast, but my RLC circuit discharges very slowly with respect to these fluctuations. So that's how I can say that my circuit will hold on to that VP voltage for a long time, for several fluctuations of the input signal. And that makes me get an approximately constant offset voltage of VP. So when at some point the VP is going to decrease, but at that time again there will be a point at which the capacitor will be able to charge back to its some will lose some charge, but at that point, whenever the diode conducts, the capacitor will charge itself back. So basically, this diode, so at the entire idea is that this capacitor is acting as an external battery. So I am adding an extra battery in there, and that battery is forcing me to that battery is forcing the entire waveform upwards. Is shifting the entire waveform upwards by an offset of Vp. So this is the principle of operation of a clamper. I understand that this is slightly more complicated than the clipper circuit or the limiter circuit. I urge you to go through this again tonight and think about this, how all these things is happening. So if you are slightly rusty with your capacitor, knowledge of capacitor, so you might actually take the help of internet, or you might actually look for clamper circuit explanations in the internet. There will probably be many. But the basic idea is this: you have a circuit in which for a small time in the negative half cycle, the diode conducts. When the diode conducts, the capacitor charges. That capacitor charge acts as an external power supply or the voltage supply. So from the next cycle onwards, you have a almost consistent voltage supply of Vp. That voltage supply acts as the offset. So whatever you're supplying to the input, at that input would reflect at the output. In addition, you have an extra Vp voltage, and that Vp voltage is your DC offset that is pushing your waveform upwards. So this is your this is the situation that you will have. All right. So, and also if you apply the second approximation, so if you do the second approximation, you will not get exactly 2 Vp, but what you would have is, so your input is this, so Vp 2 minus Vp. Your output would be somewhere like this. So this part will be Vp minus 0.7, and this is 2 Vp minus 0.7, sorry, and this is 0.7. Okay, so because of this extra 0.74, so you can again justify this by looking at the circuit. But the point is, this barrier potential or the knee potential has this effect of including some offset in these circuits. But as I said, there are techniques to get rid of these offsets. So this is basically a clamper circuit. We will do more examples in the in homeworks and tutorials so that you get these things clearer. But the entire idea is this: you have a diode which becomes forward biased, and lets the capacitor hold on, will get some charge, and then it becomes reverse biased. But around that time, you have the input voltage plus some offset provided by the capacitor. These two add up to shift the complete waveform or complete voltage signal up by an amount of equal to Vp. All right, so this is your positive clamper, and there is a negative clamper. We are not going to discuss this in detail, but the negative clamper would be exactly the same, except that your diode would be reversed. So basically, you have a diode, input voltage source, you have a capacitor, you have diode in the reverse direction as compared to you. Okay, so you have your here, and then here you have your VL, which is your VL. Sorry. Okay, so this is your clamper circuit. So any questions on clampers? Yeah, so I would request that you go through any literature you can find on clampers. So to get this thing clear, because clampers typically are a little more harder to understand as compared to clippers. But as long as you understand that this capacitor is acting as some sort of a voltage source, and we are trying to get a slowly discharging RC circuit by making RL very large, so that I have a almost near constant VB voltage, the near constant offset for throughout my time of operation. That would hopefully help you understand how this clamper circuit is working. But in terms of the circuit diagram representation, it's very simple. All you have is a capacitor, a diode, and a load resistor. Okay. So, if no questions, then we would stop here today, and we will continue with our discussion in the next class.